All right, we're starting chapter 29 in this lecture. It deals with a number of things, one of which is the so-called duality of light. Light is, on occasion, somewhat schizophrenic. Sometimes it acts like a wave, which has a wavelength and a speed. In this case, the speed is the speed of light, so-called, abbreviated or symbolized as c. And it has a frequency. This is the wave equation that we've seen put to use in our discussion of sound waves and string waves, except the speed in this case is the speed of light. We're assuming that this light is traveling through air or a vacuum, where the speed is 3 times 10 to the 8th meters per second, otherwise known as c. So we have the wave equation. The wavelength times the frequency of the wave equals the speed of light. I twisted this equation around to obtain an expression for the frequency of this wave. So far I've described light as being a wave, and it is on occasion a wave. Sometimes light acts like a wave. Other times it acts like a particle, or better yet, we say a stream of particles, which are called photons. This is a fanciful depiction of a bundle or a packet or a clump of electromagnetic energy traveling through space at the speed of light. And so we imagine a light beam consists of an uncountable number of these particles, which we'll from now on call photons, each traveling at the speed of light. Now, each one of those photons carries with it a unique amount of energy. All of the photons in a beam of light of a certain frequency f, all of them have the same energy, and it's calculated this way: h times f. What is h? I'll show you soon. F can be written, if you wish, alternatively this way. So you have two different expressions that you could use to find the energy of an individual photon in a stream of photons, which are equivalent to a wave. Let me write down the expression for that quantity h. It's called Planck's constant. H is equal to 6.63 times 10 to the negative 34 joule seconds. Planck's constant. Now, let's work a problem in which we're asked to calculate the energy of a photon in a stream of photons that represent an electromagnetic wave whose wavelength is 600 nm. An nm is a nanometer, a billionth of a meter. What is the energy of a given photon? Well, I'll put to use the second of the two different forms of the photon energy equation, h times c over lambda. There's your h, there's your c, there's your lambda in meters. And this works out to that number there in joules. It's an awkward number. We can convert this number from joules into the other form of energy, electron volts, EVs, by dividing by the number of joules per electron volt, which is 1.6 times 10 to the 19th joules. That makes up 1 electron volt. Dividing this into that, the J's cancel and an EV comes upstairs. Final result, the energy every one of the photons in a beam of light whose wavelength is 600 nanometers is 2.07 EV. When we return next, I'm going to present to you a simpler or quicker way to calculate the photon energy. That's all for now. Goodbye.